Hello, 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 everybody. I hope you're all doing well and you're ready for question 9 as we continue looking at our 2012 Euclid paper. So we got A and a B part here, both of them written. That's pretty customary for question number 9. All right, A part. An auditorium has a rectangular array of chairs. There are exactly 14 boys seated in each row and exactly 10 girls seated in each column. If exactly 3 chairs are empty, prove that there are at least 567 chairs in the auditorium. Okay. So we know it's a rectangular array of chairs. Now, the fact that we've got 14 boys seated in each row tells me that, well, there should be at least 14 sort of columns to our row. So, if we don't have so many columns, you can't fit that many boys, because it's sort of implied here that one boy per chair. Okay. So what can we do? Well, it's a written one, so let's start here by saying something to the effect of R equal the number of rows and C be the number of columns. Now, it's interesting that they say at least 567. Could there be more than one configuration that does this, that has 14 boys per row and 10 girls per column and 3 empty seats? That would be the total number of chairs. The total number of chairs, because it's a rectangle, is also RC. Well, this is one equation with 2 unknowns, so yeah, I'm inclined to believe that there are multiple ways to look at this. Now, as I said, the number of columns needs to be at least 14. The number of rows needs to be at least 10. These are nice, simple observations that you can justify, due to 14 boys per row, etc., and 10 girls per column. So you need to have at least 10 rows for those 10 girls. And it would probably have to be a bit more than that. So as it stands, if you had the minimum number of columns and minimum number of rows, you'd have 14 times 140. Now that is quite a bit away from 567. So there's probably a bit more to this that we're not seeing. This is even, this is even, this is odd. So in total, we've got an odd number here. The only way to get an odd number as a product is if both of these are odd. So I guess we could say something like R and C are odd, since RC, which is 14R plus 10C plus 3, is odd. So I guess that means that there are at least 15 columns and there are at least 11 rows, but that doesn't help. That just bumps us up to a minimum of 165. Nor should this be immediately obvious how to do the question. It is question 9A after all. So how best to approach this? Well, one thing we could do, I'd be tempted to put everything sort of on one side, because I've seen expressions sort of like this. The thing that comes to mind with this question is if you have just a nice simple product like this, you get an RC, you get something involving R, something involving C, and you get a constant. Well, what have we got? We've got RC, we've got something involving R, something involving C, and we've got a constant. Now, things don't quite match up, so I doubt that this can be easily factored, but we could attempt it. So if we know this, if we make this observation, then we could say, all right, so this is RC, but if I were to add 1 to this side, so we'll add 1 to both sides, I guess, because you can't just add 1 out of thin air. So add 1 to that side. If I subtract an R and subtract a C, this turns into 13, this turns into 9, and now suddenly I've got a nice little product here. And you might say, well, what good did that do? Well, if I were to add 13 and subtract 13 over here, then this part here is really just 13 times r minus c, so we can bring that over to the other side. Sorry, not r minus c, r minus 1. So we'll be left with 13 plus 4, 17 on this side, and 9c, and that'll be r minus 1, and then you'll take the 13, you'll subtract it from the c minus 1, so you'll get c minus 14. Okay? And we could do the same trick, but now we need a c minus 14. Well, I've got 9 c's here, so we'll just quickly grab our calculator. 14 times 9. So if I subtract and add 126 from both sides, r minus 1, c minus 14, really this part here is 9, c minus 14. So we combine these two, you'll get 143. And you get c minus 14 here. Well, now this turns into r minus 10, c minus 14. You do r minus 1 minus 9. And now we have a much nicer equation, and we can actually take advantage of the fact that r and c have to be integers. Okay? And we already know that, what, r has to be greater than 10, c has to be greater than 14. So these terms here will be positive factors of 143, and there aren't that many factors of 143. So we get some options, r minus 10 and c minus 14. We could either have one of them be 1 and the other one be 143. Okay. And what do we want? We want to show the total number of chairs is at least 500 something. Okay. Or you could have 11, 13, because these are two prime factors, that's it. Or you could swap around. You could have 13, 11, or 143, 1. But in each case, we can work out what RC must be. So R would have to be 11 here. And 11 times 143 plus 14 would be 157. You'd have to have 1,727 seats in this case. All right, what if r minus 10 is 11? So then r is 21, and c is 27. Well, there's that 567 we're looking for. What if r minus 10 were 13? Well, then you'd have 23 times 25. That's just a little bit more. That's 575. And the last one, 153 times 15. Also, just completely ridiculously large number. Okay. We see 567 is the smallest option. So we conclude the number of chairs is at least 567. And you could generalize this a bit more if you had B boys per row, G girls per row, and E empty chairs. No. I mean, that's all we did here, was we worked with equations like this. And so, what did it turn out to be? R minus 10, C minus 14. 14 was with the R, so it'll be R minus G, C minus B turns into RC minus minus GC minus BR plus BG. Okay? So now if I bring these over to the other side, I'll get E is RC minus BR minus GC. If I add BG to both sides, I'll be left with this sort of an expression. And so then you would just factor this and look at your options. So in this case, B, G, and E would both be known. So that's a cute little generalization. The fact that we got 143, which has only a couple possible pairs of factors, makes this not too bad a question to work with. That's in general what we did there, is we found a way to express this as factors because r and g and b and c, these have to be integers for this question to work. Okay, so that's A part. We got our answer with a nice little table at the end, nice short little table there. B, what do we got for B? In the diagram, quadrilateral ABCD has points M and N on AB and DC, so that we've got some ratios. So ratios here, I might start thinking, just because I'm seeing all these triangles here, we might start thinking similar triangles, but we don't quite know what's going on yet. All I know is it's going to be a geometry question, probably. Line segments AN and BN, or sorry, AN and DM intersect at P, and then BN and CM intersect at Q. Okay. Prove that the area of quadrilateral, this middle thing, is the sum of this area and this area. Okay. What can we do? Well, first, I would probably draw my own copy of this picture. Now, they say it's a quadrilateral, so I can't go assuming it's a trapezoid or anything like that. This should be a very nice general construction. Get something like that. Like that. I'm liking all these triangles here. I don't think we can guarantee that this thing in here is a parallelogram or anything like that. Although, just sort of an immediate idea here. Is it possible that... That's not a good line. Is it possible that we could split it up and this part is equal to this part, and this part is equal to this part? Sometimes this is half of the problem, is what's the best approach? Do I chop it up and show something like that? Which I don't think should work. Although we could, I believe, introduce a line here parallel to, what was it, AB. If you introduce a line parallel to AB, then where it hits here, you'll have this sort of butterfly thing. Looks like a butterfly opening its wings. And those will be equal, but then you're going to be left showing that what's left over here, all of this, is the same as this, and I'm not necessarily sure that is doable. It might be, but I'm not necessarily sure that that's doable. So that's an option as well. So break this thing up. Another way we can approach it, or we might try to approach it, I don't know if any of these are going to work. I'm just sort of spitballing ideas until I can... I find something that I think really works. I don't like that this is just a generic quadrilateral. I don't get any of that information. So I might want to rely on triangles. Okay? If I knew something like parallelograms, I'm sure the fact that this is to, what was it? It was AM is to AB, as the other thing down here, CN, NC is to ND, as this is to this. You could try doing something like this shape is part of the whole shape, but it's not going to work if you don't have nice parallelograms, because there aren't clear heights to these things. And that's the big problem is heights for my triangles are, I can drop perpendiculars down for, say, these two big triangles here, but they're not necessarily going to be the same height, because this thing is slanted relative to, say, this base down here. Okay? And if that doesn't make the triangles work nice, quadrilaterals that we're going to work with are even worse. What else could we do? Well, one thing we could do is we could try and show that this quadrilateral in here is the same as this shape, this triangle here, and this triangle here. Because, well, what do they have in common? They've got this in common and this in common, and so the remaining space, this, must be the sum of the remaining spaces here. That's an option. So certainly something we can try and do. It's not the only one we could work with. Really, you just sort of need almost anything with some overlap So are there other combinations that would work? Maybe something that doesn't have a quadrilateral in the middle. Because as I say, I don't like quadrilaterals. I'd like to, if I can, just work with triangles. Let's redraw the picture here. Slanty, nice base. Okay. Triangle down here. Triangle to the same place. Triangle up there. Triangle here. So I wanna have this sort of shape included. Now, what things is that shape a part of? And I want them to specifically be triangles. So, for example, I notice that it's part of this big triangle here. This one just sort of sitting right out. You could do the same thing with the upside down triangle. But I think this is kind of nice, this triangle here. So I've got that part, but I've also got these other bits. So if I could talk about this triangle here, well, you've got the quadrilateral, the shape PMNQ. I don't think it was PMNQ. Was it PMNQ? Oh, yeah, PMQM. Okay. So you've got the shape you want in black there, but you've also got these green shapes. So I don't want them. Now, where can these green shapes be found? And again, you want to try and focus on triangles because you have no useful information about any of the quadrilaterals you're making. But triangles and similar triangles are nice to work with. So here's this blue thing. It's got one of the two shapes we need. And it also overlaps with this, so that's nice. And if we do the same thing with this triangle over here, it's got the other bit along with this. So if we could show something like the blue triangle plus the pink triangle must be the green triangle, that wouldn't be bad, because then, you know, if you name this A, this part B, this C, this D, and this E, showing that the blue triangle, A plus B, plus the pink triangle, D plus E, is the same as the green triangle, which is B plus C plus D. Cancel out the B's and the D's, and you've got A plus E equals C, which is what we want. I like this avenue of attack a little bit better. Again, as I say, we want triangles. Why do we want triangles? Because I got no information about these not parallelograms, these quadrilaterals. I don't know if they're trapezoids. I don't know if they're parallelograms. I don't know if they're squares, rectangles. It should work regardless of that sort of information. So in the absence of special quadrilaterals, we maybe default to triangles that are a little more comfortable. So this is going to be my plan of attack. We're going to try it for a little while. If it doesn't work, we might come back to some of these other ones. Like this parallel line idea might be successful with this little butterfly thing, and then maybe you could do another one this way. You get another butterfly here or something. It might work, but I like this triangle idea better. But it took me 2-3 tries to come up with this sort of plan. So it's not something where you just sit down, look at it, and say, aha, we must do this. Take comfort in things that you're familiar with. Triangles are great. That's why I've got my blue triangle, my green triangle, my pink triangle. But it took a little bit of experimentation of, okay, these things overlap. What's going on with this? All right, so now we've got our plan there. So what would we do? And I feel like I should get a copy of this that is properly labeled so I don't have to keep going back to the picture. So D is there. N is on here. M is somewhere up here. And there's that triangle and this one. Oops. This one here. Q here. And it was P here. Okay. So if I want to work with those triangles, so we might say something like let DC be the base. Might say something like drop heights or altitudes from A, M, and B, because those are the apexes of the triangles I'm trying to work with. Okay? So we get nice little height here, height here, but they're not going to be parallel to each other because, well, AB and DC are not necessarily parallel. Okay, so we get something like that. We could give them names. I don't want to name them all H, so I guess maybe call this one A, M, and B, just based off their titles, their top letters there. Or, you know, H1, H2, H3. I don't think that's very easy to follow in a write-up. And you want whoever's marking to be able to follow your work. Okay, so what have we got? Well, then, triangle AND has an area of 1/2 base, so that's DN, times this height A. Triangle B and C, yeah, that's the pink one. B and C is going to be 1/2 NC times B. Okay? Now, if you add those up, you'll get 1/2 DN plus N. Oh, no, you can't do that because we don't have anything in common. Okay, this is going to be a little harder than I thought. But I'd like to add them up. And what's the triangle we want? DMC. Maybe I should put the apex in the middle of everything. So that'll be 1/2 DC times M. So I want these two to add up to this. That's going to be our challenge. Okay. Now, we know something about NC and ND, don't we? NC over ND is known. NC over DC is known. NC over DC. So we might say something like, I mean, usually you put the bigger thing on the top, but NC looks kind of small. So what I'm going to do is I'm going to say, so I've already used A or B. I probably would have used B for base, but let's say let C equal the length of NC. Then let DC be K times C. Okay. Because we got a nice ratio there. And then dn is k minus 1 times c. And you can see this because dc is dn plus nc. Okay, so I just took kc and I subtracted off c. So now I could take those and put them in here and everything would be in terms of c. Can we do something similar up here and maybe get a and b in terms of m? Or m in terms of b and maybe a in terms of b or something like that? So, well, let's go back and look at now. In terms of information, I've used that these two are related, although you could have done that anyway. We haven't used the fact that AM and AB are related by the same ratio. So if you called this up here, D, I guess, is the next letter we need to use, then you'd have the whole thing is KD, and you get K minus 1D for that length as well. But of course, this is sort of slanted relative to DC, so can use it, but how helpful is that? Well, we've got to use this information somehow, so I've got my base, I've got some heights. M is somewhere about here, so A, M, B. Okay. And I know if you call this D, this would be K minus 1D, and the whole thing would be KD. Okay. Now, we could say something like if we picture DC as the x-axis, AB is just a line, and we could say A, for example, is at 0A, M is at something M, and B is at something else B. Okay. So, yeah. So here's what I'm gonna do. I like this idea. I was gonna have to try and compute slopes or something, and then I thought, well, we don't know where B is above CD, but here's a better idea. If you've got a point AB, and you want a midpoint, I know M isn't the midpoint, probably, but if you want a midpoint and you have some coordinates here, midpoint can be found by averaging the coordinates, because half, the ratio between this side and this side is 1. So this is pretty common. What isn't as commonly known, although it's still a good thing to know, is that if I have a point P here, and I know the ratio of this is, say, 1 to 3, you can figure out the coordinates of P by doing 1 times W, 3 times X. I think I have this backwards. 3 times W, 1 times X, and dividing by 4. You weight it. You weight the sum, and we want it closer to A, so it gets the bigger weight. You get 1y over 4. So this sort of idea is what we're going to use, because what have we got on the top? We just have sort of some line here. But I know if this is D, this is K minus 1 times D. So if I understand the ratio of these lengths, I can figure out P. Now, I don't know, in my sort of line analogy, the X coordinates here, but that doesn't matter. You're working out the Y coordinates. So what we can say is the X coordinates are irrelevant. But since AM to MB to AB is 1 to K minus 1 to K, just giving all the ratios. Minus 1. We can find the Y coordinate of M as a weighted sum. Okay? So the Y coordinate of M is just M, but it's a weighted sum, so it's going to be K minus 1 times A, because we're closer to A, so it should get the bigger number, plus 1 copy of B all over the sum of the weights K minus 1, and 1 is just K. Great. So now, hopefully that should come back and put all this together. So if we say, all right, now update. So DAN is 1/2 DN, but what did we say DN was? Well, DN is just K minus 1C. I'm going to write it as C K minus 1. There's that K minus 1A. Now we've also got N BC, and that'll be 1/2. NC was just the little thing we called C, so C times 1, I guess you could say, B. And if I add those up, I get 1/2 C, and then you'll get K minus 1A plus 1B. Which is great, because I guess we could rearrange this and say Km is K minus 1A plus 1B. So that's the same as 1/2 C times Km. This whole thing here is Km. And then Kc is just, or Ck is just DC. So now we've got triangle DMC. So the area of DAN plus the area of triangle NBC is equal to the area of DMC. And now if we just go back to our picture here, we can appropriately label things. So we could say this was A, B, C, D, E. So A plus B plus D plus E is the same as D plus C plus D. B plus C plus D. And so A plus E is the same as C. But A is a triangle, what was it, DAP. E is triangle CBQ. And C was that, not parallelogram, that just plain quadrilateral, PMQN. Therefore, the area of DAP plus the area of CBQ is the area of PQN, which at long last is what we wanted to show. So we could put the little box that says we're done, and indeed we are. And that's question number 9. So we have just one more question to go on our Euclid paper, question number 10. So feel free to join me for that. If you tried, so I had a couple of different geometric ideas, that parallel line idea, something like this to get sort of a butterfly here. If you ever tried to explore one of those, please let me know how it goes in the link down below. Or if you had another geometric approach, it took me a couple of ideas to come up with this one with the triangles, but if you have found a way to make it work with generic quadrilaterals doing something else, by all means, let me know. In fact, let everyone know, because other people can now read your comments, and we're all the richer for it, because we all get a different way to do an interesting question. And it was interesting. So I will see you for question number 10 as we finish up our 2012 Euclid in the next video.